In this video, we're solving a classic optimization problem in which we're studying a rectangle inscribed symmetrically under the curve 1 minus x squared and above the x-axis. So the question is, what's the maximum area of a rectangle like this? In other words, as we vary the width of the rectangle, the height continuously changes and the area continuously changes. And at some point, there's a perfect width corresponding to the maximum area of this thing. So the first thing we want to get done is to label the rectangle in terms of a variable width. So we're going to call the right end of it x, giving it a width of 2x, and we're going to vary x to explore the different rectangles that can be inscribed in this space. Now to see why the area must hit a maximum, we can visualize the full range of possibilities using an animation. So when x is 0, the width is 0 and the area is 0 as a result. And then we get really skinny rectangles with small areas, and then wider rectangles with larger areas, and then flatter rectangles with smaller areas again. And then at x equals 1, we have 0 area once again because the rectangles have a height of 0. So we can think of the area as a function of x, and this function is 0 at x equals 0 and 0 at x equals 1. But clearly bigger than 0 in between, and this guarantees that there's a maximum value somewhere in between 0 and 1. So running our animation again, we can include the area function a of x as we run through all the possible rectangles, and we see that a maximum value is achieved at approximately x equals 0.58, where the area is approximately 0.77. So all we have to do to solve this optimization problem is write down the area as a function of x, then take the derivative and set it equal to 0, and we've got the location of that maximum. So a rectangle with a right edge at x has a height of 1 minus x squared, since that's the y value on this function, and the width of the rectangle again is 2x. This means the area of our rectangle written as a function of x, again we call that a of x, that's going to be 2x times the quantity 1 minus x squared. That's just the base times the height. Now we want the derivative of this thing, and I would prefer to not use the product rule here, so I'm just going to distribute the 2x into those parentheses, and that gives me a 2x minus 2x cubed. So now we can find the first derivative, and the derivative of 2x is just 2, and then I have minus, and the derivative of x cubed is 3x squared. So we combine the constants out in front, and I get 6. And then x squared. Now we're looking for this maximum value where the derivative is 0. That'll put us at the top of that hill. So we're going to set this first derivative equal to 0 and solve for x. First, we can divide a 2 out of that, and I end up with 1 minus 3x squared is equal to 0. And we can add the 3x squared to both sides and divide by 3 and turn the whole thing around, and I find that x squared is equal to 1/3. And that is a quadratic equation, so it should have two solutions. That'll be plus or minus 1 over square root of 3. But remember, in this geometric setting, x is going to stand for a positive number, so we're only keeping the positive root. All right, so there's the x value corresponding to the maximum area of this rectangle. And I want to point out that in our animation, we had a decimal approximation of this thing. And if we plug 1 over root 3 into a calculator, we end up with about 0.577 for that x value, so it's agreeing with the animation. Okay, now that we have the x value corresponding to the maximum area, we have to go back to the area function and plug that in to get the maximum area. So we're going to evaluate a of 1 over square root 3. And there's a 2x out in front at the beginning of this expression for a of x, so we end up with a 2 over root 3 out there. And then in my parentheses, I have 1 minus x squared. Well, x squared is 1/3. So inside those parentheses, I have 2/3, and I'm going to multiply that by the 2 over root 3 out in front. And that gives me a 4 over 3 root 3. Now, I don't personally have a problem with just leaving the answer in that form, but most people will insist on rationalizing all denominators. So if we multiply this by root 3 divided by itself, I end up with a 4 root 3 in the numerator. And in the denominator, when I multiply that by root 3, I get 3 times 3, which is 9. And when we plug this into a calculator, just to check for agreement with the animation, I get about 0.770. So again, our exact answer is agreeing with our computer approximation. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.